In this video, I am going to discuss about how can we draw a circle without using inbuilt functions. In If we want to project a circle in the monitor, how can we do that? Basically, we know that a circle is defined as a set of points that are all at a given distance from R. R is the radius and center is XC, YC suppose. So all the points will be rotate around that center with the distance R. R is the radius. So now we can go to the properties of circle Cartesian coordinate. Actually, we know that if we try to do this equation, x minus xc means any point minus the center square plus y minus yc, any point y value of any point minus yc square equal to r square. Why? This is why this is a Pythagoras theorem, and this is okay. You can see here in the previous slide. Here you can see if we draw a line this way, and if you can draw a right angle triangle, then this will become the longest edge of the triangle, of that right angle triangle. And using the Pythagoras theorem, we can say like this, because x minus xc is equal to what? X minus xc equal to the value of the distance from the coordinate, from the center to the value of x of the point, value of the yc, and difference between the value of y and the center value of y. We could use this equation to calculate circular boundary points. So these equations can be used as to find the boundary points. We increment 1 in x direction in every steps from xc minus r to xc plus r. Are you getting the point? Suppose, so here we increment 1 in x direction in every step. Okay, suppose xc is 6 and radius is 3. xc is 6 and radius is 3. Suppose xc is 6, radius is 3. Then 6 minus 3 means right side of the center or left side of the center to xc 6 plus 3, 9 means right side of the center, and calculate corresponding y value at each point. Means we are going to go for x direction by incrementing one value in every step from this point of x to this point of x. It means suppose this is the x-axis, suppose this is the center, then we are going to increment, or we are going to draw this circle in this way. Means we are going to increment the x in that direction, only this much portion. Okay, suppose this is the xc. Okay, this is the xc, then this is the r minus in that way, this is the r plus in that way. So this is the point in this step we can see here. Okay, next, so again same equation, so we can write that thing as like this by transferring this part in right hand side, and okay, then y minus yc equal to plus minus square root of r square minus xc minus x whole square. So y will be yc plus minus this. But this is not the base method, as it requires more number of calculation which take more time to execute. If we follow in that way, to draw a circle, suppose this is the point, center point, and we need to draw from here to here initially, then we might to go for lots of calculation, and according to this statement it is saying that it might take lots of time, and we need to follow more calculation. If we draw from this point to this point, half circle first, then we'll go in different again from this direction to this direction as per the center. Okay. Now, and also spacing between the plotted pixel position is not uniform. It says that if we do that, we cannot uniformly put those points, and the spacing between those points will not be uniform. So we can adjust spacing by stepping through y values and calculating x values whenever the absolute value of the slope of the circle is greater than 1. So here you can see is that we can adjust spacing by stepping through, means we are stepping up the y values and calculating x values whenever the absolute value of the slope of the circle is greater than 1. If it is greater than 1, then we will going to adjust the spacing, or we are going to adjust the stepping value of y, and then we calculate the x. That will be also a different method, but it will also increase the computation time. There is another thing, that is circle polar coordinate. Previously we have discussed about circle Cartesian coordinate. Another way to eliminate a non-uniform spacing is to draw circle using polar coordinates. That is the value of r and value of the angle. So we can use also those values to find the circle or to draw the circle. So calculating circle boundary using polar equation is given by pair of equation, which is as follows. This is one equation to find the x value using the r and theta. Theta is the angle from the origin with the x-axis. This is yc, and that is why we are taking sine theta here, because now we are taking y value, and y equal to yc plus radius sine theta. So this is the equation to find out the xy value given xc and r and theta. When display is produced using this equation using fixed angular step size, circle is plotted with uniform spacing. So here using this value, we might find a uniform spacing among the plotted points. So that the step size theta is chosen according to the application and display device. Now for different type of device, that theta value or step size of theta might vary, means increment of the theta might vary depending upon the size or depending upon the types of the display device or application. So here actually we are revolving around that point, that we need to plot exactly or most possible or most closest point to represent the circle. So we should not go far or too much far from the actual path of that or actual track of that circular boundary of the circle. Okay, so in that is why we try to find out the exact method to plot those points in a correct spacing and in a correct stepping value of x and y. For a more continuous boundary on a raster's display, we can set the step size at 1 by r. So here you can see, for more continuous boundary on a raster display, we can set the step size at 1 by r. Means, taking the reciprocal of radius, we can set the boundary values or plotting values by using this step size. There is another method is that there is properties of circle symmetry. Computation can be reduced. So here you can see, to reduce the computation in all these cases we have studied till now, like if we use Cartesian property, if we use polar properties, there might be also point that we might need to go for lots of computation because we have to go for all the points available in that uh, circular boundary. So now point is that how can you reduce that computation? Computation can be reduced by considering symmetricity property of circles. Now what is the symmetricity property of circle? The shape of circle is similar in its content, octet. So here you can see, suppose here this part is similar to this part or symmetric with this part and this part. So to draw this circle, if we can find out this, we can draw this part only, then we can give this value or we can use these values, whatever point we find, and just transform or find that symmetric points on other octants in this here or here, because those value will also increment or decrement or the step size will be same as per this octant. So just we need to adjust the octant value or the just plus minus things of x and y, but the incrementing value will be obviously same because it will, this symmetricity of this circle follows in that way. Shape of a circle is similar in its content. So, suppose this is the part. Here you can see this is 45. Okay. Again, here you can see if we only draw this part also, then this part will be, this part can be calculated because that is the other half of the 90-degree, and in that way this part might be symmetric with this part or this part. Okay, suppose this is the point xy and suppose this is the same symmetric point. Suppose this is the 3 minus 4 opposite point. Okay, like that way we can plot those points. Now you can see the values of x and y revolves with 4 and 3, but somewhere it is opposite, somewhere it is similar, but the signs of the magnitudes are different. So you can see what is happening in this circular track or circular boundary. So if we can calculate this part, somehow we can invert that part here, and we can invert or we can transform this part here, or we can transform this part here, or we can transform this part here. So by calculating this much only, we can achieve full computation level. So in that way we can reduce the computation. So now we are going to the actual algorithm. Taking advantage of the symmetry property of circle, we can generate all pixel position on boundary of circle by calculating only one sector. See, one sector, x equal to 0 to x equal to y. X equal to y means the line which is intersecting this octant where x and y is equal. So here it is saying that generate all pixel position on boundary of circle by calculating only one sector from x equal to 0 to x equal to y. So we are just calculating this much, then we can generate all the circle. Determining pixel position along circumference circle using any of two equations shown above still required large computation. More efficient circle algorithm based on incremental calculation of decision parameter as in the Bresenham line algorithm. You can find lots of circle drawing algorithm, or you can follow same type of Bresenham line drawing algorithm where decision parameter is used to find those incremental calculation, because we need to increment those points to find the actual points or to find the plotting points in the monitor. So Bresenham line algorithm can be adapted to circle generation by setting decision parameter to finding closest pixel to the circumference at each sampling step. So the way we try to find out the points in Bresenham line drawing algorithm, we can use that concept here also by calculating the decision parameter first, in which way we can find out the closest pixel to the circumference at each sampling step. So a method for direct distance comparison to test the midpoint between two pixels. Try to focus on this point, midpoint between two pixels, to determine if this midpoint is inside or outside the circle boundary. Suppose you want to you need to choose two candidate. You have two candidate key like this one. Okay, now this is the candidate key. You need to choose that curve. It is going like this way of the circle. Now which one, suppose this is the midpoint. Okay, sometimes this midpoint might be overlap with this one, sometimes might overlap with this one. So that is why, to find out the candidate key, we need to find out the determine if this midpoint is inside or outside of the circular boundary. So that midpoint of two candidate key, suppose midpoint of two candidate key is this, okay, this one, okay, midpoint is this one. Then whether this is inside of the circle boundary, if like this, inside of this circle boundary or outside of the circle boundary, in that way we can choose the candidate key, and that candidate key will be the floating point in the monitor. This method is easily applied to other conics also. Conics means other octant or other conic section of that circle also. Midpoint approach generates same pixel position as generated by Bresenham circle algorithm. So here it is saying that midpoint approach is almost similar to Bresenham circle algorithm, because we are dealing with the same decision parameter concept, where we try to find out the candidate key which is most closest to the plotting point circumference of the main circle. The error involved in locating pixel position along any conic section using midpoint test is limited to 1/2 the pixel separation, because we are taking the midpoint. That is why that error might be maximum to 1/2 of the pixel separation, which should not be more than 1 pixel. So try to understand this. If we use this midpoint approach, the error of getting outside or inside of the actual circumference will be at least or at max half. At least will be, or minimum will be on the same track only, on the same circumference only, but maximum will be half on inside or outside, that pixel difference. So given radius r, center xc yc, we first set up our algorithm to calculate circular path coordinates for center 0 0. So try to think it as we are taking that center as 0 0. Then we will try to transfer calculated pixel position to center of xc yc by adding xc to x, yc to y. So here what is happening? We are initially considering this as center, but suppose our question is to draw the circle along this center, then whatever thing we will get around this origin center, we just transform this to this position by just adding the values of x and y with the xc and yc. So it will just transform this circle to that direction. Along a circle section from x0 to xy in the first quadrant, the slope of the curve varies from 0 to -1. Why? Because if we try to visualize that, suppose we are going to from this to this conic section, which is 0 to this x equal to y, x equal to y. So in that way this slope will go in that direction, that is the slope will become -1. Okay, slope will become -1 at that point. At this point slope will be 0. So we can step in positive x direction over this content of 10 and use a decision parameter to determine which of the two possible y position is closer to the circular path. So now we'll go through this. F circle xy. Suppose this is a function. Function is saying that we will follow this equation to find the decision parameter. For decision parameter, we use the circle function, which is this. So if we go to the function, it will be equal to 0 if this value almost equal to r. It means almost the xy plotting value on the circle line, and this will be less than 0 if it is inside the circle, because this value will be lesser than r. This will be greater than 0 if outside the circle boundary, means this value will be greater than r, then it will be outside the boundary of actual circle. So this is the function it is using to find out the decision parameter. Above equation we calculate for the midpoint position between pixel near the circular path at its sampling step. So in this figure you can see uh, assume that we have just plotted the pixel xk, yk, xk, yk. So suppose xk, yk, then we need to plot any of these two candidate pixel, and the midpoint of this candidate pixel is this one. So now we have to find this point. This point is inside that circle line or outside that circle line. If it is inside that circle line, we might choose this pixel. If it is outside the circle line, we might choose this pixel. So these are the candidate pixel. We have just plot this one. This is the equation of the line. We need to plot which one. Now we need to calculate. So figure shows the midpoint between the two candidate pixel at sampling position xk plus 1. So at xk plus 1 there is two candidate pixel, these two. So between these two candidate pixel we need to find one depending upon the decision parameter. So now next we determine whether the pixel at position xk plus 1 or yk, or the one at position xk plus 1 yk minus 1, this should be minus 1, so that some error is here, this should be minus 1, okay, is closer to boundary. So here it is saying that this point or this point is closer to boundary. So pk, obviously our next point will be xk. This is the current point, plus 1 will increment x, and we need to find that half midpoint, yk minus half, okay, that midpoint, that according to the midpoint. Now function of the circle is given in previous slides, this, so we will use this equation. So here we plot that point xk plus 1 whole square yk minus half whole square minus r square. If pk less than 0, means this value is less than 0, then it is inside the circle. Pixel on the scan line yk is closer to circle boundary. Otherwise midpoint is outside of the boundary or on the boundary, and we select the line, scan line yk minus 1. So if pk is less than 0, we'll choose the yk value on the scan line, which is closer to the circular boundary. If it is outside of the midpoint, or midpoint is outside or on the boundary, then we select the lower point. Here you can see, if it is less than 0, then we'll choose this point, okay, or if it is greater than 0 or equal to 0, then we'll choose this point. That is what it is saying. So our incremental calculation will be like this. Now we can obtain recursive calculation using pk plus 1 and pk as follows. So we try to differentiate pk plus 1 and minus pk by plotting these points. If we put pk plus 1 in the function, this is, and initially this is the equation of pk, and then if we increment the pk by 1, means we are incrementing the xk plus 1 by 1, then we try to differentiate those plotting points by pk plus 1 minus pk, and we'll find the equation by deriving the things. If we follow the equation, you can find this explanation or equation derivation in the book also. Please follow that. Okay, if you have any doubt also, please let me know. Now after that, we find that by following this equation, so this is the equation here. Now suppose we start from 0, r, as follows. 0 r means value of y will be r. We are starting from this point, taking the origin as the center. So p naught will be this one. So p naught will be 5 by 4 minus r. Okay. So P naught is approximately equal to 1 minus R. Okay. So now algorithm is midpoint circle generation. So our equation will be this one, very important decision parameter, 5 by 4 minus R. You try to understand this, how we can find that by going to the derivation part. At each xk position starting k equal to 0, perform the following test. If pk less than 0, the next point along the circle center on 0 0 is xk plus 1 yk and pk plus 1 equal to this equation. So this equation coming from this equation or n this equation. One equation is this red one and second equation is this one. So we'll follow in that way. Two equation is important. One equation is this one. If it is less than 0, we'll follow this one, and if it is not, then we'll follow this one, where k twice k x k plus 1 is equal to twice x k plus 2 twice k y k plus 1 equal to twice k minus 2. So there remain symmetric points in the other 7 octants. Move each calculated pixel position xy onto circular path centered on xc yc and plot the coordinate values. This will repeat. So we'll try to understand it using an example. Try to go through this. I will explain it. Okay, very carefully. Suppose our radius is 10 and our center of the circle is 1 1. Only one octant we will going to try, which is x0 to xy. Now we find pixel position for octant x0 to xy from center 0 0. Initially we are not going to try from 1 1, we will try from 0 0. So our value of k, p naught will be 1 minus r initially. Initial point will be, that is why 1 minus 10 equal to 9, r equal to 10. So 1 is the simple 5 by 4. So you can take this as a 1 approximately. So minus 9. So we'll start from this position p equal to minus 9, which is less than 0. We select 1 10. When it is less than 0, we select 1 10. Okay, we select 1 10 means the x is incremented and y will be same value of r, or you can say same value of y. Okay, next, as it is less than 0, we'll select this equation. You can follow the previous slide. Minus 9 plus 2 plus 1 equal to minus 6. Then it is again 0. Then we'll select 2 10. Here we are incrementing x but not y. We are taking that x in x part. So, but it will change. You can see in the next point. Again, this equation will be same. Again, we plot the value of p1 that we got previously, and value of x2 was here 2. Then we will get minus 1. It's still less than 0. Again, we'll take 3 10. Okay, we're just incrementing the x now only, not y. Now we are incrementing again this less than 0. That is why we're taking this equation. Again, now this is 6. This is positive. Now we will take the next equation. Now we will decrement the y along with the increment of x, which is not less than or equal to, which is not less than 0. That is why 4 9, and we'll set the equation to different one. This is the same different equation, and here we can plot these values. Okay, in that way we can find minus 3. Here you can see p3 is this one, x4 is this one, and y4 is this one. Now again this is coming minus 3. So now we'll take this minus 3, that is a this is less than 0, then we'll increment 5 9. We'll at every stage we are incrementing x, but we are just calculating the y value depending on the value of p. If it is less than 0, then we'll just stay constant y. If it is greater than 0 or equal to 0, we'll stay or we'll decrement the value of y. So now p5, this equation will come because this is negative and this is again positive, and positive will decrement it, value of y will be decremented, then equation will be changed, then again positive 5, positive 5 for positive 5, we find this. You can see here next, now loop exits as x is greater than or equal to y. Initially this was greater, now loop will exit because x and y is equal, or at some cases or at different cases x might be greater than y, and in that case we'll exit the loop. In our case 7 is equal to 7. Then we will calculate pixel position for given center using equation. So we will just add the values of x plus xc. So we will increment at every point for center 1 1 with every table with every values of 0 0 that we have find out recently. Now this is the way we'll draw. Okay. So this is the way. Now your task is to find out how can we transform the same part in other octant. I can show you. Now here you can see. Now here you can see in this book the same algorithm. This is the here the equations are a bit simplified. You can, that is why follow the book also. Okay, for less than 0. For less than 0, we are taking this equation. For greater than 0 or equal to 0, we will taking this position. If it is less than x is less than y, till then we will follow this part and we increment the x plus x. But when it is ended, this will end at this point. Now this will be a recursive program, because in this function it will plot in that way, set pixel at that point. Okay, so there is 1 2 3 4 5 6 7 8. For one point we evaluated using this algorithm, we are going to plot 8 points in the monitor. Try to understand that by evaluating this function one time we can plot 8 different points in the monitor. 1 2 3 4 5 6 7 8, just by plus or putting minus or changing the value of y and x. Okay, you can see here. So we can directly, by calculating one value only, we can plot in this way 8 points simultaneously in the screen. Okay, so in that way we can minimize our computational load. So try to go through this, and this needs to be done in the lab part also, and try to understand it more. And I have to skip through the derivation part for the limitation of time. Otherwise I would have done that if we do it in physical class. But if you still want to know the derivation part in better way, please let me know. will try to resolve that over Google Meet, but I will advise you to go through the derivation part more accurately or more precisely using this book, and you will understand it if you go give some time on this. Okay, and if you have any doubt also, please let me know. Thank you.